Hello, anyone that is watching. My name is Mr. Lakin. No, I'm just kidding. So we're going to do, the reason that I am doing this video for you now is because we did not get a chance to do this on Friday as intended. This is a new unit. This new unit is going to cover this new concept, and we're going to see this new symbol finally, the other half of calculus called an integral. But we're not going to be able to use it just yet. We have to kind of go back to basics and work up to that integral, and you'll see how that works with rectangles. So these first few days historically are usually really fun for students because it's kind of a little bit of a break from the conceptual standpoint. There's not as many rules to remember, things of that nature. We are going to go over pages 3 through 6 in your packet, just to let you know. Please also note in your assignment sheet a couple other things. Number one, there's 24 pages in this packet. Some people got packets that were not printed double-sided accidentally. So that's why the packet might seem a little bit bigger than it actually is. And then number two, you might notice that on the back of the packet, on the back of the assignment sheet, there's blanks in the pages in the packet. That's because we're redoing the packets this year for a couple units. So we just have not, the packet at this time was not completed to be able to put the pages on the assignment sheet. So we'll put these pages in as we come up to them in December. The last thing that you need to note, final exams are on are going to be the week of December 16th. So please be aware that this is our last unit before finals. Historically, we usually like to give a test on this and then do finals, but because they move finals before winter break, we don't have a chance to test on this really. So we'll probably put some more multiple choice questions, especially on integral stuff, which is going to be this section on Schoology. I think that's everything I need to say about this unit. Again, the first few, this beginning part for Monday through from the 15th to the 22nd, all the way through the 26th, should be fairly straightforward. Again, students usually don't have that difficult of a time with it, and if they do, it's pretty easily cleared up if it's a one-on-one or a few-on-one work time. If that is the case for you and you were struggling with the other stuff, this is a good time for you to actually go back, look at previous concepts that you didn't understand in preparation for the final. So again, just never letting your foot off the gas that much in terms of preparation for the exam. Okay, that was enough of my introductions. That was 2.5 minutes, almost 3 minutes. Holy moly. This is Unit 5. You are going to find out what this means. It's going to be a culmination of a very big idea later. And again, we'll come back to that. But for now, we're going to go over Riemann sums. And we might do a little bit of limit summation in this video, but most likely it's going to be more Riemann sums than anything else. So let's get to what that actually is. We are going to do sigma notation. This is on page 3 of your packet. You need your packet out, please. You are also going to need a calculator out as well. And this is summation notation, sigma notation. If you've never used this before, and maybe you have, if you've never used this before though, here's how it works. This piece right here is called sigma. It's a Greek letter. In math, it means that we're going to add things up. Some terminology that I may use in class is, or a professor would use in their class, this I equals 1 part. This is called a counter, and you'll see why in a second. This is going to be I think we can call it the addend or the argument. It's the thing that's being added over and over again, so the argument. I wanted to tell you also that sometimes we call I equals 1 a counter, sometimes we call it an index, which is why you'll sometimes see these variables start off with an I for index. And that top part is just the ending part of the index, the final value, terminal value. I'll put terminal in parentheses, because the higher up in calculus you'll go, you'll sometimes find infinities on top of there. Okay, so again, this is a sigma summation notation. Let me show you how it works with just the first one, with this I equals 1 to 6 of I. The way we say this, first of all, is the sum. Actually, I should type this. Is going to be the sum. It's going to get smaller print here. Okay. All right, this is the sum I from 1 to 6. That's how we would say that. And let's do it. Here's how we add the sum of I from 1 to 6. So I is always changing, and it's changing from 1 to 2 to 3 to 4, all the way up until 6. So what happens here is that this value keeps changing, and what it looks like is, again, we have I equals 1, I equals 2, I equals 3, 4, 5, and 6. When I is 1, we have 1. Plus, when I is 2, we have 2. Plus 3, plus 4, plus 5, plus 6. And then our answer is whatever we get here. So we get 1, 2, 3, 4, 5, and 6, which is going to be equal to 21. One clever way someone did a long, long time ago by the name of Gauss. If you've ever had Mr. Freeman, you might hear Mr. Freeman say, Gauss, a baby. Is if you take the first and last numbers, they make pairs of the same thing. So this is just 3 7s added up. Okay, which is 21. All right, next. And I'll talk more about that Gauss guy in a little bit. The second one, j squared. So notice our counter, our index here is starting at 3. So what we're going to do is we're going to start out at 3. So j equals 3. You don't have to do this part. I'm just showing how the work. J equals 4, j equals 5, j equals 6, j equals 7. So now what we're going to have here is we start off at 3, and we're going to plug in 3 for j. We have 3 squared plus 4 squared plus, and again, j is 5 now, so 5 squared. And this value keeps changing based on what the counter is. Plus 6 squared plus 7 squared. Now, Gauss's trick doesn't work entirely here, so let's just get these numbers quickly. And again, you're welcome to use the calculator for this part. 49, okay, let's see here. Oh boy, that's a lot of math. Well, these two get 50, plus these two get 85, so we get 135. Okay. If there's any questions on this, well, you can ask on your own time. Let's go to this part. Again, we're doing pages 3 through 6. We're going to write an expression or formula to represent this summation. Notice here that your counter is k, your index value is k. So, and this 1 over n isn't really doing anything right now because, again, the n is not going to change the sign value because that's not the index value. Only this k will change value. So let's start off. When k is equal to 1, we get 1 squared plus 1 times 1 over n, whatever n is. This is for k equals 1. Plus, when k equals 2, we're going to get 2 squared plus 1 times 1 over n. Plus, when k equals 3, we'll get 3 squared plus 1 times 1 over n. Plus, and then this keeps going all the way up until k equals n. And when k equals n, we're going to get n squared plus 1 times 1 over n. So this would be the sum. I use this part here, which is really, really popular in math, when we have a plus dot 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 plus. It means that we have so many more terms in between the last term, the k equals 3, and the final term, k equals n, that it's just too much to write. So we do plus dot dot dot, plus ellipses, and then plus sign again to show the final term or the final last two terms. So here's what this actually looks like. We could rearrange this a little bit and see that this summation, this sigma, is going to be equal to 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared, because I'm taking each one of these n squareds, each one of these numbers squared. Now, I am very aware, and you'll see what I mean in just a minute. Actually, I won't tell you yet. Plus, now it looks like we're adding up these ones, so there's a 1 here for each of these. Let's use a different color. So here's a 1, here's a 1, here's a 1, there's a 1. So we're adding up all of these 1s, 1 plus 1 plus 1 plus so many times. How many times is this actually? Well, we had k equals 1, k equals 2, k equals 3, all the way up to k. So this is n 1s. And I'm going to put parentheses around this part here. And then finally, let's close these blue parentheses, and we're going to multiply it times this 1 over n that was on the outside, because every single one of these terms was multiplied by 1 over n. Now what we're going to find out later in this next picture here is that if we add up a whole bunch of 1s n times, that just turns into n. If we add up this squareds, this is going to be a formula you're going to see in a minute. It's going to be n, oh, I messed that up. It's going to be n plus 1 times 2n plus 1, all divided by 6. And again, you'll see that on the next page. I do not expect you to know that yet. This is still times the 1 over n on the outside. So finally, what we're going to get is n plus 1 times 2n plus 1 over 6n plus 1. And the way I got that was I multiplied the 1 over n to both sides. This is kind of a jump and a preview of where we're going to be going. It's going to be mostly algebra for this part. There's not really a calculus concept tied here yet. There's no limits, there's no derivatives, there's no integrals. This is just some pre-calc and algebra. Here's where we're going with this. So if we have some numbers, some c value, and we added from an index of 1 all the way up to n times, where we're going to get when I equals 1, we get c. When I equals 2, we get another c. When I equals 3, we get another c, etc. all the way up to I equals n, we'll get a c. So the value of this, the value of I equals 1 to n of c is equal to n times c. And I put the proof in the wrong spot. These two parts should be switched, but that's fine. The asterisks, I just noticed that we have some asterisks here for our summation formulas. Let's see what that says at the bottom. Ms. Schwartz made the packet. Ms. Schwartz says you need to know these. So you got to know them. All right, linear one. Let's see what this looks like here when we start adding things up. When I equals 1, well, first of all, let's do it over here. When I equals 1, we get 1. Plus when I equals 2, we get 2. When I equals 3, we get 3. And we keep going in this way. When I equals n, so we keep going in this way, dot, 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 plus, dot, 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 plus n. And I'm not really seeing a pattern here. Well, I'm going to tell you that the answer is going to be n times n plus 1 over 2. And this actually has a really cool proof with it, one that I like. So let's just take, if it was from the sum of I equals 1 of n, I equals 1 to 4, not to n, but this time to 4. Well, that means that we would get of I. That means we would get 1 plus 2 plus 3 plus 4. Okay, good. Well, the way I could look at that is geometrically. For the 4, I have 4 dots. For the 3, I have 3 dots. 1, 2, 3. For the 2, I have 2 dots. 1 and 2. And for the 1, I have 1 dot. Okay, now what does that do for me? Well, it actually makes a nice rectangle. You don't see a rectangle. Oh, my wife cursed. Hold on just a minute. So my wife's okay. She's a little sick too now. Okay, so we have 4 blue dots, 3 green dots, 2 red dots, and a purple dot. Obviously, I could add all these up pretty easily, but if I'm talking about a huge number, I don't really want to draw these geometrically each time. So let's look for a pattern here. I see something that I can do here. I'm going to put these black X's here. Okay. Oh my gosh. He is making a rectangle. Look at that. That is a beautiful rectangle. And what that means is that now I can take the total number that I have here, which is 5. Sorry, this is a 5 by 4. And if I take 5 times 4 and I divide it by 2, I get 10. Do you know what 1 plus 4 times 2 plus 3 is? I'm sorry, 1 plus 4 plus 2 plus 3 is? It's 10. So whenever we have an n value, like a 4, what we could do is we could plug it into the equation here. When n is 4, we can get 4 times n plus 1, which is times 5, and divide it by 2 because we can take the half of the area of this rectangle and we'll get our answer for what the summation is without actually having to add up every single term. It's a good formula to know. N times n plus 1 over 2. For more complicated reasons, the n's I squared, and I'm going to stop this video and do another one in just a minute, so that way this isn't so long. From I equals 1 to n of I squared, that is going to be n times n plus 1. That's false. Oh, goodness, Mr. Lakin. That is going to be, no, that's right, n times n plus 1 times 2n plus 1 divided by 6. That's a big formula. It's a little bit harder to prove. You can't do it so nicely like a rectangle. That's not true. You can kind of do it with a rectangle, prove that formula with a rectangle, but it's a little bit more cumbersome. All right, let's look at I cubed. This one is actually going to be, you should recognize this one, n times n plus 1 over 2, but the whole thing is squared. So it's basically the linear form, but squared. That's going to be if you have your addend, your argument is cubed. Now the constant multiple rule is a fun one. The constant multiple rule means that when you have some k value, some number multiplying this value here, the argument, what you can do is you can take that k outside of the sum and just multiply it when you're all done. And that kind of makes sense because if you look at it expanded, just to make sure you're clear, when I equals 1, we have k times a sub 1 because I is 1 now, plus k times a sub 2 because I is 2 now, plus k times a sub 3, plus dot dot dot, plus all the way up to k times a sub n. You'll notice that each of these k's, each of these terms has a k in it. Again, you wouldn't have to prove anything like this. I just wanted to show you anyways, because that's common, especially if you take a higher math class. Okay, so this k times a sub 1 plus a sub 2 plus a sub 3, well, this part, the a sub 1 plus 2 plus 3, all that part is right here, and the k is on the outside. In short, if you have a number that's not just being multiplied to every single term in the summation, you can take that number outside the summation and just focus on what you're adding. This is a good one to know. I would put this also on the list of things that you should know. Okay, I'll continue the other part 5 and 6 in the next video.